Hey folks, this is me, Vishwas Narayan. I welcome you all for this podcast. This is a kind of a podcast where I'm just trying to demystify what is it all about when we are now perceiving a technology with a quantum touch. It's always there where quantum computing was not a hype to one extent, but there was a reason for us to go behind it. And there was a reason for us to get to know what is the potential of quantum computing in the present classical computing. And there is always a difference that it brought. And there's a reason for us to think about what is the next future thing that we really want to achieve using quantum computing. So Johnny Hooyberghs is here. I think there's no other person other than Johnny Hooyberghs. Trust me to just give you that in-depth understanding of what a Microsoft infrastructure can be. Trust me, don't worry about the advanced things that we might be talking in the podcast. We'll make sure that we'll add the overlays on the YouTube and we'll actually have a lot of discussions on it. But understand the way in which this technology needs to be pursued by the industry. I think he's going to give you an amazing set of insights for you guys. So make sure that you learn it. So thank you so much, sir. It means a lot.
I'm very happy to be here. Thanks for inviting me. Maybe I'll just introduce myself a little bit. My name is Johnny Hooyberghs, indeed. I live in Belgium, and I'm a software consultant, and that's what I do all day. I'm doing mostly Microsoft-related technologies like .NET and Azure Cloud and Azure DevOps kinds of things. And actually, I just from the start on, I want to tell you that I am just a guy like you are, and like you people at home are. I am interested in all these new technologies. I really like to learn about them, but I'm not some kind of master in quantum computing. A couple of years ago, I went to a conference in Belgium and I saw a talk about quantum computing, specifically targeting what Microsoft is doing with quantum computing. And I attended this talk and I did not really understand everything that the speaker was talking about. So I decided to dive in myself. I started buying books, reading from these books, trying to understand what was going on. And then basically, I think about 6 months after, I decided to do a talk myself. I was like, okay, I'm a developer. I want to make sure that quantum computing can be explained to like the general developer audience. These are people that don't really know about like mathematical things. They don't really know about these pure theoretic physics related stuff. They know a little bit, but they don't know the depth. They're not PhDs in physics or mathematics. So I really wanted to talk about the subject, but try to make it understandable for people like me, people like you, software developers, basically. And that's how I rolled into this interesting world of quantum computing. I prepared some talks. I did these talks on many conferences. I wrote a book on quantum computing, again, specifically targeting the developer audience, explaining in a normal language and not in these extreme physics stuff. And yeah, that's where we are today. Still very interested to see where the future of quantum is going towards. And yeah, I'm happy to be here again.
Yeah, that's true. Thank you so much for being here. So let's just talk about it. You told that you have been working in DevOps, and of course, I do. I'm deeply honored that I have a chance to work on a problem statement on DevOps. And there is always a reason for us to think back at what did we do as a software engineers and things like that. So I just wanted to ask this question: what's the role of philosophy in science today? It's like we have everything, but yet we are understanding in a different fashion. But there's always that one common understanding that always lies behind the production environment, or else something like how can we leverage this hardware or the software? So what is the role of philosophy in science today?
I agree. There's so many things today that we can do in software development. We have so many options, so many tools that can help us. It seems like the possibilities are endless. But yeah, why do we need quantum computers? Because for some reason, there's still many problems that we cannot solve today, because it's just too hard. For some reason, I remember this time when I was a teenager that I was already interested in software development, basically because I was creative, but I was lazy. So I just tried to create things on a computer. So I didn't need to use my hands too much. So I just was very interested in creating like small computer games or small algorithms. And then a teacher came up to me, and he had this cool problem. He asked me, if you have a chessboard, there's like a piece on the chessboard called the knight. And the knight can do, like represented by the horse, it can do very specific jumps. And he asked me, can you make an algorithm, or can you write an algorithm that makes the horse jump around and visit each square of the chessboard only once, and then filling the entire chessboard? And I was like, that's a very easy thing to try to solve. You just write a computer program that tries all different possible routes, and then after some time, it will tell you what the route is to jump on each squares without visiting a square more than once. So I wrote the program, started to write the program, and I finished, and I ran the application, and it searched for minutes, it searched for hours, and it didn't give me an answer. And I thought I made a mistake. I think I was 15 years old or 16 years old. And after some time, I even let it run overnight, but it did not give me a solution. And I thought I made a mistake, so I abandoned the issue, and I just went and played outside or with my friends, whatever you do if you're 16 years old. But then only when I got a little bit older, I realized that these problems are exponential in nature. For even a classical computer to solve something that seems this easy, there's only 64 squares. But if there's only 64 squares, it's like an exponential problem. With each step you take, there are so many more possibilities of other routes you can take, and it's a number that goes into the billions, and it's very hard to comprehend. But it is the case. So yeah, there's still so many problems that we are just not able to solve on our classical computers today, because they grow exponentially when we add a few variables, and that is why we are still searching for newer technologies, newer computer systems to help us solve these problems.
Yeah, that's the role of philosophy, right? There's always that understanding that we need to have, like, we can't know it all, and also we know the fact that we are supposed to stop at one given point of time. So that's where the philosophy of the science comes in. So yeah, let's just talk about the quantum hardware a little bit. There's always an decoherence, that's denoising of the signals and things like that. So there is always a noise in the quantum information, which is always considered. But yet, we are now relying on a photonic based hardware, which is more enthusiastic for us to learn something which is more quantum, because that's really an approximation that we are going towards. So what is it all about when we think back at the quantum computing world, which is much more complex and yet to be demystified? And yet we have a Moore's law which says that your transistor goes exponentially. And there is no reason for us to not to say that, yes, we are packing in more transistors, which is going more exponential, but yet quantum has a different ability to be given, right? That's where we are now talking with respect to qubits and things like that. So what is it all about when we are considering the potential of an quantum hardware with respect to the classical hardware? Can we reach to a point where quantum hardware surpasses the performance of a classical hardware that we are just working on today?
That is indeed the ultimate goal. So today the answer is no. Basically, quantum computing is, of course, based on the quantum physics, and quantum physics is a theory. It's not only a theory, it actually exists, of course, but it's something that is already more than 100 years old. Scientists in the beginning of 1900 were already investigating and doing experiments based on the real small particles in our world, the microscopic particles, the quantum particles, and they saw that things were behaving very differently than from our macroscopical world. An atom behaves very differently from the chair you are sitting on. So that theory is already very old, and it really exists. We already did many experiments throughout the years, throughout the century. So we know that quantum physics is real. And then already in, I think, the end of 1970s, 1980s, onwards into the 1990s, scientists were thinking about, okay, how can we leverage quantum physics in computing to help us forward with performance? So again, the theory, purely the theory of quantum computing is already 50 years old. But of course, we never had the power to build these physical quantum computers. In theory, we knew we can create qubits based on these microscopical elements. And then when we have those qubits, we can do specific operations on them to help us reach solutions to very specific problems, but we were not able to build them. Now today, and already for the past, I think about 10 years, we have been building very small quantum computers that have only a few stable qubits. And then they tell us that we can do this for a small number of qubits. But then indeed, what you were saying is true. When we start adding more and more qubits to that system, it becomes more unstable. Because of course, in order for us to leverage all of these very specific quantum properties like entanglement, like superposition, these qubits need to be very isolated. They cannot come into contact with our real world, but that is almost impossible to do because everything comes in contact with our real world. In quantum computers today, different companies are leveraging different kinds of materials to try to put something into superposition. Some companies indeed are using photons, others are using electrons and specific properties on them. There's even other companies that are looking at bigger objects like entire atoms or even crystals to try to do the same thing. We are basically just experimenting and finding something that works and is also a little bit more stable than what we can do today. Again, when you look at these very small particles, they cannot come into contact with our real life. So they put them into a vacuum so that they don't have air to come in contact with. They drop the temperature to almost absolute zero, so that the lower the temperature, the less activity something has, so that it's more still in space. But then there's like radiation coming from outer space that hits us all the time. We cannot shield something like that. It goes through everything. So it's really hard to put like a tiny particle into a complete isolated world. And that's the reason why when we add particles to a system, they are in close proximity. They start interacting with each other. They have like magnetic fields and stuff like that. So it's just very, very, very hard to do. So when we are building quantum computers today, we are talking about number of qubits, which is basically number of microscopical elements that we can use to act as a qubit. But when we add more, they become more unstable. So we need even more to do some error correction and stuff like that. Because we have quantum decoherence. When we put something in superposition, after a couple of microseconds, it goes out of superposition by itself. And we cannot have that happen when we put something in superposition, and it needs to be in superposition for an amount of time during our algorithm. It needs to stay in superposition unless we tell it to be measured, and then it can collapse. But of course, when we have a couple of qubits, we use those qubits, they are in superposition, and then they decohere by themselves. They go out of superpositions by themselves. Yeah, we basically lost our data, and we cannot continue with our algorithm. And that is why we need more qubits, so we can use them in parallel. We can do error correction. We can run our algorithm in parallel on a different amount of qubits at the same time, so that a number of them will survive and another number of them they will decohere, and then we need to create some smart algorithms that can tell us, okay, this is something we can trust, this is something we cannot trust. And again, the problems that we can do today on physical quantum computers are so small that we can also implement them on classical hardware, and it will even run faster and cheaper. The quantum supremacy, basically, it's a term you hear all the time, means that we can indeed create a physical quantum computer and an algorithm that runs on top of it that supersedes, that is more powerful than our current classical hardware. But we are not yet there today. Companies are still investigating materials that can help us to use as qubits. in order to make it more stable, they are trying to create quantum computers that have more stable qubits, so that we are able to run those algorithms. So yeah, we are not yet there today. We are still doing many experimentations. Lots of smart people are still trying to build these physical quantum computers. But of course, you and me, we can already start learning about it, because maybe in 10 years or maybe in 50 years, we don't know, we will have the first real useful quantum computer that actually supersedes our classical hardware, and then we are already ready. We know a little bit of the basics, and we can already start learning more about it, already starting to run our algorithms that we already know on this hardware, and we have basically we have some years to already teach ourselves what it is all about. I am quite confident that we will get there eventually. Again, maybe in 10 years, maybe in 50 years. We don't know when, but we will get there eventually, indeed. And it's true, like you said before, quantum computing can be more powerful than classical computers because of how we are using these things. If you look at a classical computer, we have a number of transistors in a CPU that basically tells us how powerful the CPU is. And CPUs today have billions of transistors, and we already left the millions. We are now in billions of transistors, billions of these little switches inside of a small chip that are able to deliver us the power and do some operations on numbers to give us the power to do whatever we want. But it's billions. But if we want to double the power of a current CPU, we basically need to double the amount, the number of transistors. If we now have, let's say, some random number, 2 billion transistors, and we want to double the power of that CPU, we basically add another 2 billion transistors. So we have 4 billion transistors. And that is also quite hard to do. It is, of course, expensive, because you have probably twice the cost, and it is also very hard to do and to keep it in this small chip. And that's why CPUs always go smaller and smaller in the transistor size to fit more transistors inside of the same chip, or maybe make the chip a little bit bigger. But we cannot create chips that are the size of a house, of course, because they will get too hot. And then for quantum computing, it's completely different. When we are encoding data into superposition, we can basically represent all different possibilities of this data within a number of qubits. That's the idea. And in order to double the amount of different states that a superposition can collapse to, we only need to add one single qubit to double that amount. So that's a completely different story. And that's the exponentiality of nature. And when you have a problem that grows exponentially, well, a quantum computer, when you only add one single qubit, the power also grows exponentially. So this hopefully can help us solve these exponential problems. Again, if quantum computing becomes more stable and we have a quantum computer that contains 50 qubits, we only need to add one qubit to make it twice as powerful. We only have 51 qubits. Of course, today, with all the problems we have, adding one single qubit also exponentially grows our problems to keep it stable. So we have that issue, but hopefully we can someday solve that issue. And by some smart physicist, he maybe invents some new kind of way to encode this superposition data into something. Maybe it's photons, maybe it's something else, maybe it's ions. Doesn't really matter. Someday we will find a solution, and then we can really leverage that to create these powerful quantum computers. Again, hopefully.
Yeah, that's true. That's true, because we have a reason to find a new solution every single day, right? There's always that one big thought process that goes behind building anything that we are talking about, quantum or AI. But we still have quantum supremacy, which is still a buzzword, which is not yet achieved. This kind of an jargon for the quantum world, and it just really blew the minds of what can be the potential of a quantum system or a quantum computer when it's fully furbished and built over a course of time. So we now are dealing with something called as quantum machine learning. As a next level complexity. Like it's it's like you're it's like AI is something like we are now trying to build a brain. We have built 10% of it. So now let's just add quantum to it. So I feel that, AI was just an humble attempt from any person who just wanted to understand what a brain was. But today we have quantum machine learning. So quantum machine learning, should we keep it questionable claim, or should we keep it as an optimistic view, or should we keep it as something more cautious for the world tomorrow? Because we are now trying to break in code, the same old encoding and the decoding what you talked about. We are now trying to build more of the security aspect. Of course, when you think of a classical computer, CPU had a different encoder and decoder, where even if you have a digital code, it has to be converted into hexadecimal. That's what your CPU asks for, and that's what your CPU understands. So what is it all about when we talk about quantum computing? Should we keep it questionable, a cautious one, or should we just make sure that we just demystify some more and we just build on something which is quantum and machine learning? So what is it all about when you hear the word quantum computing having the potential to do the same thing of what machine learning did using the classical algorithms as well as classical hardware? So what is it all about when you think of that part of the quantum world?
Okay, so yeah, I did not yet investigate into all of these, again, as you say, these new things and specifically quantum machine learning. I'm just trying to learn the basics first. But I do agree with you that, yeah, quantum today is really a buzzword. Many companies are using quantum just for marketing purposes, and of course, because quantum is so hyped at the moment, all of these big companies are working towards it. And Microsoft is trying to build their own quantum computer. They are working on that today. Google is doing the same thing. IBM is doing the same thing quite successfully, I propose. I expect, and many other companies are doing the same thing. And indeed, the ultimate cool idea would be to be able to simulate a human brain, and the idea there is basically the same as with medication. Today we are using classical computers to build models, like, for example, in artificial intelligence or in machine learning, or just stuff like when a pharmaceutical company tries to create a drug to solve a problem, solve a disease, which is basically a problem in the human body. They are creating models and they are trying to run those models on classical hardware. And it's the same with the human mind. So many things are going on inside of your body and inside of your mind that for a classical computer to be able to completely simulate this, it is just too hard. We need much more capacity to store data. We need much more processing power to reach that same amount of power. If you look at, again, if I look back on this medical thing, on these pharmaceutical companies, the reason we are still doing animal testing today is because we basically cannot simulate medication on a human body with our computing power today. We cannot. We only can do very small aspects, and we can try, okay, when we introduce this drug to our body, what will happen with our cells? How will they react on that? We can simulate it in like a very small example, but again, we need animal testing because we cannot simulate the entire model. Because when you look into your body, there's not millions of tiny little cells and particles. There's billions and billions and billions. There's so many things that will interact with that drug that it's just too hard to do. Again, when you're standing in the middle of the road and a truck comes towards you and you look at it, in a split second, your body knows that you need to jump away. Again, this is intelligence. This is, I need to save my life and I need to jump away from that truck, and that happens in a split second. That is the neurons in your brain very quickly coming to this conclusion, because in your brain, again, there's billions and billions and billions of little cells that work together, also in a quantum way. As I told you before, our world is quantum, so everything works quantum. So all of these companies that are working on a quantum computer, their basic idea is, if your brain works quantum, if your body works quantum, and this is able to do all of these things, then if we build something that is also quantum and we are using the same logic as in real life, we are basically not per se simulating it. We can just do it in the same way and then hopefully solve these problems much quicker. So that's the idea. If we will ever get to that, that's the question, of course. But indeed, if we do machine learning or AI, and we are trying to simulate a human mind, well, if we do it quantum, we have more chances because our real brain works quantum. Of course, neurologists, so people that are learning and working with the human brain, they still have many questions. We only grasp the surface of how our brain works. So they also need to do some more investigation and some more experiments to really know how everything works in order for us to also do the same thing in quantum. But because the quantum world is so different from the classical world, all of our algorithms, we also need to rethink them. We cannot just port a classical algorithm onto a quantum computer, run the same algorithm on a quantum computer and hope that it will be more powerful. No, we really need to start from scratch, write our algorithms from scratch, and really think in a different kind of way about this. And then indeed, hopefully, we will get to the point where quantum machine learning can really be more beneficial to what we are already doing in classical machine learning. But yeah, I think we need to start from scratch, and we need to think about these algorithms again from scratch. There's so many people, intelligent people in the physics world that are already working on this, and of course, they have their knowledge from the physical world. And we have our knowledge as software developers, so we need to work together so that we can hopefully find new algorithms that can help us with these problems and can really benefit us running on quantum computers. So I hope that was an answer to your question.
Yeah, no, that was an answer, because there is always that hype which goes behind like quantum machine learning. But have we ever really understood what does a black box called as a neural network mean to us today? Because everybody knows how to write a code in TensorFlow. Everybody knows how to write code in this and that. Like, of course, ML.NET is there. There is an amazing set of frameworks which are coming up. TensorFlow is also supported by a .NET framework today. So if you go for the Nugget packages are already available for you. So there is always a need for us to have some sort of a matrices, like something like Turing test became the amazing set of matrices for all of our machine learning problem statement that we have today. So Turing test is like, how can we build AGI very close to what Turing actually designed to be? Or else how is the Turing test going to be passed? There are some chatbots who have actually surpassed that standards of being less than, of course, they are considered to be a less than AGI, what we can think, but they are very close to AGI. That's an approximation that we can see from that algorithm, which is already built on that H5 model, PT model, or else anything. So there's always a metrics to measure the success of anything. Like the Turing test is for the NLP. So how can that chatbot or a machine, which is behaving like a human, surpass this test and be the superhuman for the tomorrow's world? So there is always that urge from our side, like what can this answer? Like yes, what can quantum computing can answer? So what is it all about when we are looking for a matrix which can really say the potential of that entire system that we're going to build, as that entire algorithm that we are just moving towards? It's like order log n, things like that for the classical computing. So, and also, what is it all about when we are trying to think about what are the questions that this entire infrastructure can solve for me for the tomorrow's world? Because there is no metrics that we know that this quantum computing has this amount of potential, and there is no metrics to say this is going to be the questions that it can truthfully answer. So what is it all about when we are still in the dilemma of matrices and yet to demystify what can be answered using this infrastructure?
Well, that's actually why I like that some of these companies are already designing the tools for us. For example, Microsoft, because I work with lots of Microsoft technology, so I know that they are building quantum computers and quantum simulators on top of their Azure infrastructure, and they are building the tools for us developers to write code and to already try to understand these things. IBM is doing the same thing. They have their physical quantum computers, they have their cloud environment where you can use them, it was IBM Q Experience. I'm not sure if that is still the thing today, because it's been a couple of months since I looked into that. But they also have their own language. They use Qiskit to write quantum algorithms, and Microsoft is using Q#, for example. Again, I told you quantum computing today is not very useful yet, because we can still use classical computers, and they are basically still more powerful than the quantum computers we have today. But the tools are already here, so we can already learn the tools, and we can already write small things in those tools. And we can write algorithms for very small problems that we know we can also solve on a classical computer much more easy. But we can try to create quantum algorithms that successfully run on a quantum computer today that only has a couple of qubits for these very small problems. The algorithm from Shor is a very good example, where you have prime factorization or factorization of a prime factorization of large numbers. It is basically used for our security today, and lots of people are talking, yeah, quantum will break our security in the future. That's many years in the future still, but today the algorithm from Shor, which was designed in the 90s, we can implement that in these languages that are already available today, and it will work. It will factorize these small numbers into their prime factors, and it will be successful in most of the times. And we can compare that with the classical outcome, and we can compare those two results, and we can see that it works. It reaches the same result. So we know that the algorithm works today, but it is not useful because we cannot use it on large numbers. But these algorithms are written in a way that we can easily scale them. We just need more qubits, but the algorithm itself, the basic structure of the algorithm is the same thing. We just need more qubits in order to run it on these larger numbers. So we know that the potential is there. We have the tools today. We can use those tools to prove that the potential is there, that the algorithms work on a small scale, and that they can be scaled up to also support these larger scale problems. And again, that is why I'm very happy to work with this already as a developer. For Microsoft specifically, I'm using the same tools that I use every day during my job when I'm doing software development. I'm using the same tools to do quantum, only the language is different. I can run it on my local laptop for very small problems. I can play around with these results. And because it's a simulated environment, I can even do debugging. I can put breakpoints in my code. I can look at the quantum state. In real world, you cannot look at a quantum state, because when you look at a quantum state, it will collapse and you will basically lose that state. But in a debugging environment, which is just run by mathematics, of course, it requires lots of memory, but you can do it. You can. My laptop, for example, has 64 gigabytes of memory, which is a lot for a laptop, but I can allocate about 30 qubits in Q#. I can do all kinds of things with these 30 qubits, and I can put breakpoints, and I can see the quantum state, and I can learn from that. Okay, if I do this operation, it changes my quantum state in this way, and then I can learn from that. I can develop my algorithm more and more, and hopefully I can reach whatever goal it is I'm trying to reach for, again, a small part of a bigger problem. And then hopefully my solution or my algorithm will scale when the problem gets bigger, and I can just run it using more qubits, which are not available today, but hopefully they are available in the future, which makes my algorithm powerful. Just like that.
There's always that reason behind me saying that there is a difference between what you explain and difference between what you are actually seeing in the quantum world. Like the experience and the explanation might get different. Like like you might experience something on your 64 gig system, which is stashed with so much amount of compute, and also somebody might feel something else. Probably this compute equivalence that we are building, probably that might also be a reason that we are not able to give a complete explanation for the phenomena of quantum computing. And now we have a definition of plausibility, which is also coming up. Like, there is always a reason where we are actually moving towards the plausibility of this event using the deep learning or the machine learning algorithms. We know that this existed. What if this existed? What can it be? And there are something called as explainable AI. There is something called as an AI, which is supposed to be more secure. Like, in the DevOps world, we have a talk going on saying that what's your metric for security of your entire environment. So there is always a reason for us to find something new. So now we have a state-of-the-art compute, which is now solving the problem of not actually thinking about more of the compute, but yet let's just go on and build on something which is more feasible for us, like something like an AI model can be built, it can be deployed, it can be scaled. We have found that solution. So what is it when we talk about the scalability of the systems with reference to the classical computing for the quantum world? Like, are we able to scale it to that extent? Because what I feel is like problem statement which quantum want to address is much more complex than what we have right now. Like we had the need for serverless, we came with the serverless, but what next? So there is always a reason of saying what next in the quantum world as well. So what is it all about when we talk about the definition of complexity, intelligence, and the new plausibility that we are just coming up with the machine learning with respect to the quantum world? So what is it all about when we are compiling the theories that we had in the classical compute to the quantum world?
Yeah, it's a very good question, and unfortunately, I'm not able to answer that because I didn't yet look into quantum machine learning as much, also for classical machine learning. So I cannot really answer that. I think it's very important that today we still acknowledge that quantum computing is in its very early stages. We first need to get them more stable in order for us to be able to transform all of our current knowledge from the classical computing into the quantum world. We can already try that in theory. We can already try some. We do some experiments again in theory, and then when the physical quantum computers are powerful enough, we can try to move all of those stuff from classical to quantum and see if it can really help us. It's also very clear today that for classical computers, we are already used to using the cloud, using these cloud providers to help us scale our problems much more easily. Because when you run your server farm on premise, it's much harder to do it for us. The cloud providers can do it for us much more easily, or they can provide us the tools to do it much more easily. Of course, they need to do the groundwork. But for quantum, it looks like it's going to be the same thing. The quantum computers will not run in your on-premise environment. They will run in the cloud, and we will be able to use them as long as the cloud providers offer them to us, and they will get better over time, and we will be able to use these better quantum computers. So again, hopefully this will help us with also scaling our solutions to problems, because when we only have one quantum computer running on premise, we only have that and we are limited to that. But in the cloud, again, the cloud provider can unlock all the potential for us in a much more easier way, and we have the tools to use that. So yeah, that's the only thing I can tell about that. But yeah, today I think we should really focus more on like still the basic development of physical quantum computers, and if that is going forward, everything is still good. But of course, we need to find solutions to that before we can go into how to migrate our very difficult classical problems into the quantum world, basically.
There's always that reason for us to move towards the quantum world, because we know that classical computer can't really have that compute intensity in order to understand what is this drug development all about. So there is always a reason for us. So now there is a requirement to have a prerequisite before we enter this world, right? You are a software engineer, you attended a conference, and now you fell in love with the quantum world. Of course, you did DevOps, you did .NET development for a while, and it still remained the same for you. The process still remained the same for you because the infrastructure was already ready and it was available for you. But to a person who doesn't know what is this quantum world, what's an ultimate prerequisite? Because there is entropy, Hilbert space, behavior of the atoms, whatnot. This unrealistically, there is no end for the theory of the quantum, where Einstein's theories are not yet being demystified. They're still yet to learn from the quantum world itself. So what is it all about when we talk about the ultimate prerequisite for the quantum world? When somebody wants to enter it, how can they enter it?
Well, it's a very interesting world, and it is a bit confusing. I agree, but the good thing, as I told you before, I am not an expert in quantum physics, and I'm not an expert in mathematics. I'm a software developer, and I know a little bit about these topics, but not enough to really dig deep into how the physics work. But I don't think that is necessary. And I talked to a couple of people from Microsoft and outside about quantum computing and quantum physics, and they basically told me that don't worry about that. We also don't know the answer to all of these questions. Things like entanglement and superposition, we know that it exists because it is proven from experiments. So we know that it's there, and we know that we can use it. But deep down, like for example, entanglement, nobody knows how it works. We just know that it works. It exists. We can use it. We can leverage it. But scientists only have theories about what is actually happening in that process, but these theories are not yet proven. We have no idea how two particles can be entangled, can be very far apart, and they can collapse to opposite states at the exact same moment in time. We just don't know how that works. We only know, again, from experiments that it always works, that it works like this. So don't worry about those things. Don't try to, or unless you want to do a PhD in physics and you want to win the next Nobel Prize, then you should maybe look into that. And then hopefully when you find a solution, you will be very successful with that. But again, if you're a software developer and you want to work with quantum computing in the future, don't worry about those things. That's the reason why I'm diving into this subject, again, for me to learn more about quantum computing, but also to teach other people and to comfort them. Don't worry about all of these deep down physics. That is also the reason, again, why IBM and Microsoft are creating these tools for us. They are adding layers of abstraction on top of this pure technical stuff. They want us to be able to work with quantum on a more higher level abstraction, just like we do with programming languages these days. And so if you look at a programming language like Q#, deep down, it's just putting qubits through gates like we also do with classical computers. In classical computers, you have a bit, you put bits through gates like the AND gate, the OR gate, the NOT gate, the exclusive OR gate, stuff like that, and you get a result from that. In quantum computing, it's the same way. The gates are different and the bits are qubits. But you don't really have to know that in the future. Like when you learn a programming language like Java or C# today, you don't need to know about this pure logic stuff. You just have your methods and your classes. You use your structures, like your loop structures and your select structures. This is like a higher level way of thinking on programming. And with quantum, it's going to be the same thing. Today, we are still putting qubits through gates, but we can build operations and functions on top of that have more clear names. Like if you want to do a Fourier transform, a quantum Fourier transform, you can implement this by putting qubits through gates, or you can just call a method that has the name Fourier transform and then put some arguments with that method, and that will just do that low-level stuff for you without the need for you to know about these things. So that is why I very much like the fact that these tools are already out there. And to come back a little bit to your question, it is, for me, it was basically first learn about a little bit about quantum physics to understand what these phenomena actually mean. And then when I kind of understood those, I was looking into the mathematics, because you need to know a basic about the mathematics, because it's much harder to represent a quantum state than it is to represent a classical state. A classical state is very easy to represent. It's 0 or 1 or some combination of those, 1 1 0 0 1 1, but it's always that. And you can basically do that from the top of your mind. If you have an AND gate and you have 2 inputs and 1 output, if you put 1 1 in an AND gate, we all know from the top of our head that the result is going to be 1. So that's very easy to do. But in quantum computing, when we talk about superposition, we are talking about vectors in vector spaces in linear algebra, and we can try to draw it on a little piece of paper how the vector is oriented in this space. But when you do combined states, when multiple qubits are in superposition, calculation. We are not able to do it like that. We need to use linear algebra. We need to write down matrices, like combined state matrices, which can become very large over time. So it becomes really hard to calculate from the top of your head. So you need a little bit this basic linear algebra understanding to be able to help you debug your problems. If you're debugging your quantum state, you need to be able to write it down, to calculate it manually, so that you really understand what is happening. So that is the process that I went through. And then just look at existing quantum algorithms. Try to find easy algorithms, try to understand what they are doing, how they are leveraging these quantum phenomena to really find a solution to that problem. Again, that's what I did. And I don't really want to do a commercial on the book that I wrote, but I just want to tell you that what I wrote down in this book, maybe I should share my screen. Can I do that?
Yeah, you can do that, sir. You can do that.
All right, let me quickly try to do that. Like this. You disabled it, so you need to enable it first.
Okay, I'll give you the permissions. Sure, perfect. Yes, I've given you the permission.
Alrighty.
Yes.
Yeah, so yeah, in my book, I'm trying to use the same process that I went through. So I divided it up into multiple parts. Again, this is an introduction to Microsoft quantum computing, but it explains what quantum computing is about, but it's using the Microsoft tools. But it should be the same for all quantum computers today, for all universal quantum computers. I divided it in three parts, where in part one, I explain the theory of quantum computing, and we look at what is quantum computing, why should we need quantum computing, and how are we going to do it, basically. So this explains the physics behind it a little bit with some examples. The second chapter is then about the qubit and the quantum state. So this tells you about what a qubit is and how a quantum state, so that superposition state or that 0 or 1 state, is encoded inside of a qubit. And then in chapter 3, we go into how to combine multiple qubits together, put them through quantum gates to do operations on them, and build quantum circuits or algorithms from that. So this is, for me, was a very good basic introduction into what quantum computing is. Again, I bought some books. There are today many more interesting books to learn about the basics, but when I did it like 3 years ago, most books were very theoretical and very mathematical. And it was very hard for me to understand all of this mathematics. That it's been more than 10 years for me that I did school. So a lot of those little details I forgot about. So it was very hard. So again, I hope with this kind of introduction, with the basics of everything, you have just enough knowledge, but not too hard to really understand what it's all about. Then the second part is basically about how to use the tools from Microsoft to work with quantum computers, how to install the SDK, how to build your first very simple quantum algorithm. How to use the language itself, what are different language features, and then finally, when you simulate quantum applications, quantum algorithms on your local PC, how can you test them, how can you debug them by putting breakpoints in your code, stuff like that. And then in the final part, there's chapters about existing quantum algorithms. So just like I told you, try to learn about them, try to understand the ones that are already out there. That is already quite hard to do. There are simple ones that are quite useful, but because they are simple, it's easier to understand, and then build your knowledge from going from simple algorithms to more difficult algorithms. And yeah, basically in this book also I have a couple of appendices that will teach you a little bit about trigonometry, which you need to calculate probabilities for collapsing qubits. You have complex numbers which you need to encode the qubit state, and you have some linear algebra basics that you need to do calculations on top of your quantum state. If you do operations on your quantum state, what happens to that state? That's basically some linear algebra there. So that is how I taught it myself. These basics already helps you to understand what it's all about. And then the next step, you can start things like quantum machine learning and what that looks like. But first, you really need to know this basic stuff.
Yeah, that's true. That's true, because it's all about that. So yeah, perfect. So yeah, last two questions from my side. So what is the nature of quantum circuits and a quantum algorithm that you are thinking should have been existed today? And also, what is it all about when we are talking about when we are designing something using the math of the quantum? Because now we had tensors, we know how the tensors work. Now, what is it all about when we are talking about the qubits in terms of the quantum world? So, what should have been the nature of the circuit and the algorithm today, according to you?
Oh, that is a very difficult question. Yeah, today I'm not sure, because yeah, again, I'm only looking at this from a software perspective, so I really don't know what the hardware of a quantum computer in detail looks like. I have the basic understanding that they're trying to use like these physical particles to encode that quantum state into, and which is very hard to do. But I have no idea how hard it is to do, and I also don't have an idea where we are at today, because companies, they always communicate these things to the outside world. We have reached this many qubits, but what is actually going on in their laboratories, I have no idea about, because I don't work with these kinds of people. So yeah, it's very hard for me to answer that question, where we should be at today. But I think the most important thing for these algorithms is to help us to solve problems that we are not able to solve today. Again, I really don't like the fact that pharmaceutical companies, when they create drugs, that they are basically experimenting, because they are not able to simulate what is 100% going on when they introduce some substance into your body, and they're doing animal testing, stuff like that. I really hope we can solve these things, because it takes a long time to create a drug. We need to do many experiments, because we don't know beforehand what it's going to do, what it's going to be like. We know, of course, a little bit, but we just don't know the very details. So I really hope that quantum computing can help us more with these kinds of problems. I also hear that, for example, banks and insurance companies are looking at quantum computing to help them to create more personalized insurance policies. Because today, an insurance policy is depending on so many variables that it's also very hard to create a very personalized insurance policy. Because yeah, are people smoking, yes or no? How is the people's health? Is it good? Is it bad? Which diseases or which things do they have? Some people need to pay a little bit more for their policy. Other people need to pay a little bit less. So I know that insurance policies are already looking at quantum computing, because they can input all of these different variables, and then they can calculate somehow what for one specific person the best policy would be to help them, of course, the insurance company itself survive. And because they of course they want to give people money when they need it, but they don't want to do it too many times, because then they will go bankrupt. Yeah, I'm still in conflict with myself. Is it a good idea to create these very specific policies for people depending on what they mean, or do we need to keep it generalized? Like some people pay a little bit more and they don't have any issues, and other people pay a little bit less because they do have issues, so that basically we help each other in that way. So I think, I'm not sure, but I know that many companies and there's many aspects for using it to help us solve these problems, again, that we cannot solve today because they're just too exponential in nature. And of course, I would wish that all of those problems could already be solved today. But yeah, that's not the case. So we just need to wait until hopefully quantum computing will become really a thing that works, and we can use that for these professional problems that we face today.
Yeah, that's true, because it all goes back to the stats of what is being observed in the today's world. Something like, I can say you this, okay? Hyperbaldiness. Like, I have a little bit of baldness here and there, but like, I'll say what the statistics says that there is a ratio of this amount of people to this amount of people. It's common that there is hyperbaldedness and the things like that. It's not about that. And also there is all, of course, there is always a medical thing. There's always an institution which comes into the picture about what they need to sell, what they need to market, and things like that. And also, like when you think of something called as a disease, there will be a medication, but it depends on every person. So it's just that statistics which comes into the picture, the ratio of like who survived and who did not, what was the condition and what was not the condition. And it's always there. So it takes a lot of time even to understand what's the behavior of that drug is all about.
That's true.
Somewhere down the line they will come back and say that it's a little bit more of a side effect. Like there is an annotation in the medical world saying that every drug has its own side effects. If it doesn't have a side effects, it's not a drug. I'm like, what? I'm here to get solved with one disease. I'm not here to add on a disease.
Yeah, exactly.
So there's always a reason for that. So you have seen how the DevOps rolls in the market. It's the buzzword to some people. It's actually bread and butter to some. It's basically the definition of an institution to be, because Netflix has amazing DevOps culture. I can't deny the fact that they don't have an amazing DevOps culture. Netflix has amazing. Microsoft, AWS, all of these institutions have their own definition for DevOps. So forget the fact that there is an existence of DevOps in the world of quantum computing, but like, according to you, how much should we automate with respect to what we have in the current scenario? Like, we have some things, so how much should be the automation that should be going on in order to achieve the quantum supremacy that we might be desiring for the tomorrow's world? So my question is all about like, how will an automation look like in a quantum computing world?
I don't think there will be much difference between the classical world and the quantum world, because as I told you before, today we are already using the same tools for classical and for quantum. We are using the same cloud environments. For example, on Microsoft Azure, we have services that can help us to deploy our applications, and Azure Quantum is part of Azure, and we are using the same tools to talk to Azure Quantum when we are using Azure CLI to make our Azure environment do something or change something. We use the same Azure CLI to deploy our quantum algorithms into Azure Quantum and to run them on Azure Computing. We are using Azure Storage to store our input and output data for our quantum algorithms. So in the future, this will evolve, of course. It will become more integrated, because it's very important to know, by the way, that when we are creating these quantum programs in the future, it will always be a combination of classical parts and quantum parts. We are not going to write an entire program on a quantum computer. No, we are going to create a classical program that will run a very specific piece of code on a quantum computer. It will input some data, it will run the algorithm, and then it will output some data. And then we use that output again from the classical world to do something with that. So I think the entry point of our applications will still be classic. And there's only a very small part of our application that we will offset to a quantum computer, let him or let the quantum computer run the problem, give us some solution, and then we can incorporate that solution into our classical program. So because of that, I don't think there's going to be much change. We will just write our code. We will still use source control to manage our code. We will write unit tests. Today in Q#, you're already able to create unit tests for your quantum algorithms so that they can test your code if it runs how you would expect it to run. Yeah, I think it's going to be the same thing. And of course, the idea today in DevOps is to automate as much as possible. So we can do the same thing. If you want to deploy your quantum environment, how many quantum computers do you need? How much processing power do you need? You can just write scripts to be able to allocate those resources for you at a specific time, deploy your application, run your application, all automated by using pipelines. I'm very, very confident it's going to be exactly the same thing.
That's true. That's true. I think, guys, sorry for not asking too many of the technical questions, because Quantum is huge. I'm very new to the quantum world, and I just wanted to explore something on my podcast, and this is what it was. So thank you so much, sir. It was an amazing set of insights that you shared today. I think it's going to help a lot of folks like me to understand what quantum world is for the tomorrow's world. And thank you so much, sir.
That's no problem. I'm very happy to be here, very happy to help you, and good luck with all of your quantum endeavors. And I'm going to do the same thing. I'm going to keep on learning, keep on reading, and hopefully we will have so much fun in the future with this topic.
Yeah, thank you so much. Thank you so much.